Hi again. In this video, we will try to solve the longest common subsequence problem using dynamic programming. There is a sort of a recipe to this, and hopefully it is not as intimidating as you have been told. And hopefully by the end of this video, you get a grasp on how to solve these kind of problems. So there are 5 steps, and we will go over them obviously step by step. The first step is to identify an optimal substructure. So an optimal substructure is the solution to a sub-problem, a smaller problem than what we already have. Your solution to the bigger problem can be solved as a combination of these smaller sub-problems. So for example, when we did the Bellman-Ford algorithm, we saw that the shortest path that we can go from say S to another vertex, say U, if we have found the shortest path to that, and we see that the shortest path to go from S to V is something that we can construct out of this previous solution that we have found, then that is something we can leverage in our solution itself. So that is the optimal substructure. Interestingly, this is common between greedy algorithms and dynamic programming algorithms, but the way the substructure gets constructed into the main problem is what differentiates between the greedy solutions and the dynamic programming solutions. Little more about that later, but first let's see how we can come up with the optimal substructure for our problem of the longest common subsequence. So right now we have, let's say, 2 strings, and let's use some notations to help our formulation. The notation is using this subscript here. So if we say y subscript 4, that denotes a prefix of the string y, or a substring. That's actually a substring, not a subsequence. Starts at the beginning of the string and ends at this particular index here. Remember, we are indexing from 1. So y4 means you are looking at the first 4 characters of the string. Our sub-problems will be able to find the longest common subsequence, or the length of the longest common subsequence for any for any prefix length xi and yj based on some smaller subproblem. And the way we would capture that information is by putting it into a 2-dimensional array C, indexed by I and j, which is the length of the prefix that we are looking at. Let me give you some examples so that you know what xi and yj we are talking about. So let's say I have x2, meaning I have a prefix of length 2 that is going to be AC, and y3, let's say, that is ACG. And the longest common subsequence, let's call that C of 2, 3, is going to be the length of the longest common subsequence between these 2 strings. And we can solve it by hand and see that the length of the longest common subsequence, or the longest common subsequence, is AC. So its length is basically. So our optimal substructure that we are using here is basically the length of the longest common subsequence for different prefixes of x and y. This is a good choice because there is a lot of overlapping subproblems. As such, for dynamic programming problems, you require that there are a lot of overlapping subproblems, which is when it makes sense to use things like tables or memoization to store information about past results so that you can construct the final result out of these past results. Let's see an example of why this is true so that it's very clear why the subproblems overlap and why dynamic programming is a good choice for this. So we already found that the longest common subsequence between x2 and y3, which is C of 2, 3, was 2. The reason why we have overlapping subproblems is because we can use C of 2, 3 to go to find the longest common subsequence between x3 and y3, which is basically this substring and this substring. We can also use it to find the longest common subsequence between x2 and y4, which is basically this part and this part. So that is where you have overlapping subproblems, meaning we can extend it either in the direction of x or in the direction of y and reuse this result to come up with the longest common subsequence for those strings. The next step is to actually use these overlapping subproblems and define a recursive formulation of this length of the longest common subsequence to leverage all of these properties that we just saw. So how do we do that? Let's consider different cases here. So, using the longest common subsequence of prefixes so that we can expand it further along. So let's assume that we already have the longest common subsequences for all the cases where the substring of x is smaller than I and the substring of y is smaller than j. So we have everything like x, like c of I minus 1, j minus 1, c of I minus 2, j minus 2, and so on and so forth. So right now we are trying to find out how we can expand it to c of I comma j. Now there are two cases. Let's suppose that xi and yj are the same character. Now we can get the longest common subsequence of going from any of the previous steps that we have constructed to finding c of I comma j by adding 1 to whatever we had in c of I minus 1, j minus 1. Meaning, let's suppose that this was the substring that we had already found the longest common subsequence to, meaning we already have c of 4 comma 6. Now we are trying to find c of 5 comma 7, and it turns out that I and j are xi and yj are the same character. So that means we can expand or extend our longest common subsequence by one character, meaning whatever we found here plus the a. So we can say that c of 4 comma 6 plus 1 is equal to c of 5 comma 7. That seems pretty intuitive because we're expanding the longest common subsequence with a character that is common between the two. And we are actually moving in terms of prefixes, so this is something that actually appears after what we have already found. Great. Other cases when they're not the same. Now this is a case where things become a little bit more tricky, or we have to really think about what to put over here. So let's say these are two other strings, x and y, and we see that I and yj are not the same. How do we then expand how do we then reuse any of the previous solutions to come to the solution for, say, c of 5 comma 7? How do we construct this in terms of previous solutions? Just because we have already constructed previous solutions, we have c of 5 comma 6, we have c of 4 comma 7, and we have c of, let's say, 4 comma 6. So that is, we have everything to do with this substring and the I and j substrings, meaning I minus 1, j minus 1 in all three directions. Can we leverage this information? We can't go from here onwards because we can't add 1 to our substring. But we can look at these two subproblems that we had previously solved to come up with the solution for c of 5 comma 7. How? We can either keep the case when t is not involved and retain the substring of this entire prefix and the prefix of x without using t, or we can do the same thing with y, meaning we don't use the prefix that has a and we use the entire prefix that has x. So we either pick this one or this one. Which one should we pick? The one that is the maximum, obviously, because we are interested in the longest common subsequence. So essentially we are looking at the longest common subsequence that you got if you didn't have t, or if you didn't have A. And that's pretty much it to actually expand into this solution. That seems pretty intuitive. It's not at all intimidating at this point. So in terms of formulating it as a mathematical expression, we would end up getting something like this. C of I comma j is C of I minus 1 j minus 1 plus 1 if we have the same character, meaning these two characters are the same in both the strings, so we can expand the longest common subsequence by 1. And if we can't expand it by 1, we choose the maximum of whatever we got, either in the x direction or from the y direction. That's the base case here is if the length of the strings are 0, in which case your longest common subsequence is 0. That's kind of a base case.
Okay, now let's actually use this recursive formulation to use dynamic programming and solve the problem. So the algorithm is pretty intuitive. It basically just uses this recursive formulation that we saw and puts it into a nice algorithm. We expand the longest common subsequence by 1 if we see that x of I and y of j, meaning the characters that we are expanding into, are the same. And otherwise, we choose the maximum of what we had by ignoring one of these. Of course, we pick the maximum of those because that's the one that gives us the best solution. Okay. Naively, the running time is O of n comma m, because we are going to solve this for all the prefix lengths between the x string and the y string. Here n is the length of the string y and m is the length of the string x. So that's pretty much it here. Let's see how exactly it rolls out in terms of how we maintain this C variable in that two-dimensional array, and we see how we expand it as we look at x and y. And a good way to do that is by actually drawing out a table that looks like this. Put x on one side and y on the other side and see if we can expand it. Initially, we put all the 0 row and columns into 0, meaning where the substring size is 0, we put 0 there. And then we start expanding. We can either do it row-wise or column-wise, doesn't matter. I prefer to do it row-wise. So let's start there. So first thing we are looking at is C of 1 comma 1. Now let's see which of these cases it applies by checking if x of I and y of j are the same. Of course, they are the same because we are looking at A, which is common. So at that point, we look at the diagonally previous entry and we are going to add 1 to it. So we end up with 1 here. Next thing we will look at is C of 1 comma 2 because we are going row wise. And in that case, we check if A and C are the same. They are not the same. So we end up either picking the one that is higher coming in the x direction or in the y direction. Turns out that one is higher, so we keep that there and then we can proceed. So going through the animation, we can see that we add 1 here all the way to the end because we didn't find any other A's there. And then when we look at the C thing, the first one becomes 1 because x of 2 and y of 1 are not the same. But here when we start looking at C of 2 comma 2, again we see that x2 and y2 are the same character. So we have to expand it from the diagonally opposite entry, which is 2 plus 1, 1 plus 1, which is 2. Now when we look at C of 2 comma 3, we compare x of 2 and y of 3, which is C and T. They are not the same. Now we have to make a decision whether we come from here or from here. It turns out coming from the x direction is better because it's higher. So we end up putting 2 here. Continuing on with the animation, we actually see that that's what happens. And as expected, in this row, we will see that we can expand the longest common subsequence by 1 when we reach the character G because x3 and y4 are the same. So when we get there, that's where we come from the diagonal and added 1. Um, Interestingly, if you don't have any common characters, you would not end up expanding the longest common subsequence. You would only be copying over the terms. If you have common terms, that is when you expand the longest common subsequence by 1, and that comes from the diagonal. Keep this in mind because this is important for reconstructing the longest common subsequence. Continuing on with the next term, again we get the same thing, and we end up finishing the table in this way. Excellent. So what is the length of the longest common subsequence? We look at the last column, last row entry, which is 3, and that is our length of the longest common subsequence. Perfect. So we found the length. What do we have remaining? We need to keep track of some additional information, or we need to reconstruct our steps or redo our steps back in the table to find out what is the actual longest common subsequence. This is written as if needed, because in some cases you may only be required to output just the length of the longest common subsequence, and you don't actually need to output what the longest common subsequence is. So if required, we would do this step. To do this step, first we would construct the table, and then we would need to figure out how we got these entries in the table, and we work backwards and construct the longest common subsequence. So start from the final entry, work backwards. So every time we are at a final entry, we can check how we got to this entry. There are there are actually 3 ways that we can get to this entry. One is either we just copied over the term from the previous substring in the y direction, or we copied it over from the x direction, or we added 1 to the diagonal element. We can add 1 if the character is the same, and if not, we came from the previous step. So here we see that 3 must have come from the 3 above. So same way we work backwards. Here we see that we found the matching string, so we should have come from the previous step. Similarly, we go backwards. We go backwards in some direction or the other and figure out this thing, that this should have been the longest common subsequence. As you might have noted, there was a tie at this point, and depending on how you code it, you could either break the tie by going up or going to the left. Both of them would yield you the same result, but the only place where you should be careful is while crossing diagonals, because this diagonal is different from this diagonal, mainly because of the entry that you're comparing. So as long as we can keep track of diagonal jumps, that's where we keep track of whether or not we have added an element into our longest common subsequence. That's pretty much it. This is the longest common subsequence. And there are the examples that are in the previous video. I will add those in the description as well. So you can feel free to work them out using the dynamic programming solution and see if you find the same solution as what you did by working it out by hand. Hopefully it's the same. So once we have the dynamic programming problem, the solution and the pseudocode that finds the longest common length of the longest common subsequence, and the algorithm that can actually find you the longest common subsequence by working backwards, you would need to actually write the code. And it turns out that whatever we discussed is actually not very far from how we would code it up. We didn't do that bad. The pseudocode is actually pretty good. So yeah, I mean, the basic solution is right here. We did do this in O of n times m complexity. If you want to do better, it's a pretty challenging problem. And I would leave that as an open exercise for you to figure out if there are solutions that help you do that, or if you can come up with a better solution. Maybe if you come up with a better solution, you become really famous by finding a good solution. So that's pretty much it for how we solve the problem using dynamic programming.